Okay, this is lesson 12 on capacitor, energy, and dielectrics. I'm sorry, 11 there, but that's actually lesson 12. So here we're going to learn how to describe how a capacitor stores energy and also describe the effects of adding a dielectric material to a capacitor. Okay, so here we can see this is sort of a sketch of a capacitor being charged, and we looked at a demonstration of that in the previous lesson. And uh, so what is the energy that it gets? So it gets charged, it collects charge um, from the battery onto the capacitor. So how do we describe the energy um, that that the capacitor has gained now? Well, you can recall that electric potential energy we found by multiplying the charge by the electric field and the displacement. Okay, and so so the electric field and the displacement, we also recall that's equivalent to the potential difference. So we could say also put this in terms of the potential difference. So the electric potential energy is Q times the potential difference. So as a small amount of charge, say dQ, is given more potential, then the capacitor, the energy of the capacitor will increase, okay, by du. So it'll be dQ and delta V. And we can put this in terms of capacitance because we know that capacitance is charge over potential difference. Okay, so we could say then that this is instead of voltage, we could do charge over capacitance. Okay, and so the total energy transferred from the battery to the capacitor, we can then do the integral of this. So I'll say energy of the capacitor UC. Okay, so the capacitance is a constant, so we can pull that out of the integral. And then we can integrate over Q. And so then we'll end up with Q squared over 2C. And we can put this in terms, a lot of different terms, depending on what type of energy we want to know. So we took it out of potential difference and put it into terms of capacitance. Well, we could go back and put it in terms of potential difference if that's useful. Okay, so we have Q squared 2C, and so then Q is then C delta V, square that, over 2C. And then what we end up having is, say, 1/2 C delta V squared. Okay, and we could describe in terms of the electric field strength too if we want to. So if we have the potential is 1/2 C delta V squared. Well, what do we know? The electric field inside a parallel plate capacitor, or the capacitance inside a parallel plate capacitor, is epsilon naught times the area of the distance between the plates. Okay, so we can do 1/2 epsilon naught area or the distance. Oops. Delta V. Well, and then delta V. What do we know? Delta V. Delta V is also the electric field times the distance, and so call that ED. And we see that the D's will cancel out, or actually, oops, got to square that. So one of the D's will cancel out, and then we'll be left with 1/2 epsilon naught area, one of the D's, and then the electric field squared. So a few ways to find the potential energy, the electric potential energy within the parallel plate capacitor. So depending on what we want to know, so we have Q squared over 2C, 1/2 C delta B squared, or 1/2 epsilon naught area, distance between the plates, electric field squared. Okay, so let's try an example of this then. To what potential should you charge a 1 microfarad capacitor to store 1 joule of energy? Okay, so what do we have here? Potential is V. 1.0 microfarad capacitor is C. And 1 joule of energy, that's our electric potential energy. So if we're looking for V, right, we want to know what's the potential or the potential difference. And we know the energy and the capacitance. Well, which one of these relationships will help us? Okay, so potential is equivalent to, looks like this one, capacitance. We know, and we're looking for that. We know that. Okay. So 1/2 capacitance delta V squared. And so we solve for delta V, and we get square root of 2C to U over C. Okay, and so 2, potential energy is 1 joule. The capacitance, 1×10⁻⁶ farads. And I get about 1414 volts. Okay. All right. So capacitors, they're important elements in circuits, and the reason is because we could store and release energy. And so we saw in an earlier video in the previous lesson that we can slowly charge up a capacitor and then slowly release that charge, right? We did that into a light bulb. But we could also release the charge rapidly. And we could see this in keyboards. So each key has a little capacitor under there that when you press it, it sends a rapid release of energy, electrical energy, to send that information. And the more dramatic use of a capacitor is with the defibrillator. I actually try to restart somebody's heart. So just have one little demonstration of this showing the rapid release of charge. All right, so we've seen the small release of charge. Let's look at the rapid release of charge. Okay, so in the back here, it's not a parallel plate capacitor, but it is a capacitor, 100 microfarads, and it's got 2 terminals on there. And so I have a very high voltage power supply here because I'm able to charge this capacitor up to 800 volts. So quite a bit. And so what I'll do here is I'll charge it up, and the reading on the bottom is in kilovolts. So I'll go up. I think I go up to like 500 volts. And I'll turn it off. So now the capacitor is charged, and what I'm going to do here is I'm going to touch the terminals with this big screwdriver. And so that basically is shorting the capacitor. We call it shorting. We'll learn about shorting a little bit more when we get really into circuits. But it just released all the energy very quickly, all at once. Okay, so we can release the charge at any particular rate. There's multiple ways we can do that. Okay, so that's energy storage, releasing energy. There's also something we call energy density. Okay, so the energy density of an electric field, like inside of a parallel plate capacitor, is the energy stored between the plates divided by the volume that stores it. Okay, so if we have two parallel plates here, we can sort of try to visualize the volume. My fancy art skills. To help with notability, making everything nice and neat for me. Okay, so now we can sort of see that there, we sort of have a cube there, and so there's a certain amount of energy produced by the electric field, and there's a volume there. Okay, so the energy density is the energy per volume. Okay, and so this is for the parallel plate capacitor, it's energy per area of one of the plates times the distance between the plates. Okay, and so we use a little u, subscript e, to represent energy density. Okay, so the energy divided by the volume, area times distance between the plates. Okay, and we also said energy. The capacitor's energy, we had that. We were able to put that in terms of the electric field. Okay, so we can actually use that to put this not in terms of the energy, but actually the electric field strength too, if we want to. So the UC was 1/2 epsilon naught area times distance electric field squared, right, over area times distance. So area and distance cancel out, and so you can also put this and say it's 1/2 epsilon naught d squared. Okay, so depending on what if we know how much energy there is, we can use this, or if we don't do that, we can, and if we know how much electric field strength is, well, we can use that if we want to. So okay, so the units of energy density are going to be joules per cubic meter. Okay, because we have energy per volume. Okay, and so what is the energy density if we have 10 joules of energy stored in this parallel plate capacitor, and if of 10 centimeter by 10 centimeter plates that's spaced 20 centimeters apart? Okay, so we can say separated by 20 centimeters. Area is 10 centimeters by 10 centimeters. And we have the energy in the capacitor is 10 joules. Okay, so then we'd want to use this relation to find the energy density. Okay, so C over area times distance between plates, 10 joules. Area is 0.1 meters by 0.1 meters. And the distance would be 0.2 meters. And so I get 5,000 joules per cubic meter is the energy density in this parallel plate capacitor. Okay, then the last thing we'll look at is what we call dielectrics. And so if we have a parallel plate capacitor, if we say, let's say that this parallel plate capacitor, we place it in a vacuum. Okay, so remember, a vacuum means that we don't have any air, we just have empty space. And we could do this in the lab really easily. And so when the capacitor is fully charged, we represent the potential difference as delta V with a subscript 0, so delta V naught. All right, so this is just how we represent the potential difference in a vacuum. Okay, and so then the charge on the plates, right, we'll have plus Q here, minus Q here. And so the charge will just represent a plus or minus Q naught. Okay, and then the relationship, the capacitance is Q naught over delta V naught. Okay, and so a dielectric is a material that's an insulator within that we place in an electric field. And so if we place one between the plates, it doesn't change the charge on the plates, but it does decrease the voltage. Okay, and so let's say I have electric like this that I put in between the plates. Okay, and so what happens? Remember that the electric field lines in the parallel plate capacitor point from the positive plate to the negative plate. Okay, and so when a dielectric's placed in the parallel plate capacitor, this induces an electric field within the dielectric itself, and this electric field points in the opposite direction. So the electric field induced in here would actually be, there would be positive charges this side, negative charges this side, and so those electric field lines would point the opposite way. Okay, so we see we have a net. Now our electric field weakens, right? Because we have one pointing one way, one pointing the other way. So they're like subtracting. And so what this does, the effect this has then is on the capacitance is that it decreases the voltage. Okay, and if we decrease the voltage, then that means we're decreasing the capacitance as well. So we'll show you another demonstration of this. Okay, so we've looked at this demonstration a couple times, but I didn't show you the whole thing. So now in the end here, I'm going to place a dielectric material. So you can see I'm sliding it in there. It's a piece of acrylic, and it has water in it. And so we see as it goes in, the voltage goes down. Okay, so water is actually can be a dielectric, and the effect is we reduce the electric field when it goes in, and it reduces the voltage, which increases the capacitance. Okay, so that's one way to get more capacitance is to insert a dielectric in between your plates. Okay, and then so often with with these plates, with these capacitors that are rolled up, right? They sort of have two plates, or two pieces of metal, and then a material in between. Okay, so even paper would do, and roll it up, and you can actually, that would be a capacitor with some dielectric in between the plates. Okay, so the electric field gets weakened, and the capacitance increases. When we place a dielectric in between the plates. Good. So here are some examples of dielectrics. So we can see that the vacuum, basically, each dielectric material has a what we call dielectric constant. Okay, and we symbolize this with the Greek letter kappa, which sort of just looks like a little K, and it's epsilon naught divided by the electric field. And so materials that can easily be polarized, like we saw that there's a polarization that gets induced in the dielectric material. And so the ones that can be easily polarized have large dielectric constants. And so we see that the dielectric constant of a vacuum is just 1. Okay, and that's what we called, we said in a vacuum it was just V, delta V naught, C naught, Q naught. And so we can see here that pure water is 80. Okay, so it is a good electric. It is a good dielectric because we were able to see it decrease the voltage and therefore increase the capacitance. Okay, and so in a vacuum it's 1, so we can say kappa naught is 1. Okay, and so placing a dielectric into the capacitor increases the capacitance by a factor equal to the dielectric constant. So basically, the capacitance is just kappa times whatever the capacitance would be if it were in a vacuum. Okay, so let's try an example of this. And so in this example, we're going to look at a cell. Okay, and so a cell often has, we know has a cell wall, but often it behaves like, the cell wall behaves like a parallel plate capacitor with a dielectric in between. Okay, so what is the capacitance of a 50 micrometer diameter cell with a 7 nanometer thick cell wall whose dielectric constant is 9? So cells, we know, come in many different shapes and sizes, but for our purposes in this course, we're just going to model cells as spheres, and so many cells are mostly spherical in nature. So we can apply this model for our purposes. So let's say we have a spherical cell, okay, and it has a diameter, okay, of 50 micrometers, or a radius of 25 micrometers, and it has a cell wall. Okay, so basically it has another. Basically, this is the wall, right, in between here and here. And this is 7 nanometers thick, okay? And so you get a picture of this. We're seeing it in 2 dimensions right now, but you get a picture this as a sphere. And so essentially, the walls of the cell wall behave like parallel plate capacitor, and what makes up the cell wall behaves like a dielectric with a constant of 9. And so what then is the capacitance of this cell? So we know capacitance with a dielectric is the dielectric constant times whatever it would be. Oh boy. Times whatever it would be in a vacuum. Okay, and so if we're treating this like a parallel plate capacitor, then the capacitance is epsilon naught area over the distance between the plates. Okay, where our area of a sphere is 4 pi r squared. Okay, so our capacitance will be K, epsilon naught, area over the distance. So K, dielectric constant is 9, epsilon naught 8.85 times 10 to the minus 12. Then the area, okay, so area is 4 pi r squared, so 4 pi radius is 25 times 10 to the minus 6th meters, square that. And so the area is 2 times 10 to the minus 9th square meters. And the distance between the plates is the cell wall thickness. So the 7 nanometers or 10 times 10 to the minus 9th meters. Okay, and when I did that, hopefully you get the same thing. Oh, I didn't do it, so we'll do it together. So if I did 8. Oh, I must have forgot to multiply by 4. Okay, that's a mistake. Okay, so I get 8.9 times 10 to the minus 11th. Remember, capacitance is measured with farads. Okay, so now you should be able to finish up homework 5, and there's another example problem that can help you out here with energy density. You still need help with that. And so did you learn to describe how a capacitor stores energy? Okay, so we came up with a couple different ways to figure out how to determine the energy within a capacitor, okay, depending on whether we know the potential difference or the electric field. We could always, even if you didn't know this, you could always, know what the electric field is, so you could plug that in and you would get this, and you would get this anyway. And then energy density, right, the lowercase u, okay, we found a couple ways to find how we find that. And then we learned to describe the effect of adding a dielectric material to a capacitor. And so, so we found out that relationship. It was just whatever the constant, dielectric constant was, times whatever the capacitance would be in a vacuum. And we saw that it increases the capacitance, decreases the voltage, and weakens the electric field. Okay, so that's it for lesson 12 and everything going along with chapter 26.